Hi, hello, welcome to our presentation. My name is Mario. I will be going the introduction. Next slide. So for our project, we wanted to see if there was a correlation between NCAA statistics, which is a college basketball players, and to see if they would have a good performance in the NBA, basically to see potential stars. The context for this is it was inspired from a experiment done with machine learning in the 90s from wine tasting, basically to see if they could predict a good wine using machine learning. And that is what our project is inspired from. The stakeholders from here are basically scouters from information assess could potentially replace or help scouters in various types of sports, not just basketball, but we are doing this in regards to basketball. And basically take large amounts of information from the data set and can output potential stars in a given sport used how an individual wants it to be. Of course, given that data is provided. Next slide, please. The data sets here used are 6 from Kaggle and 1 from Data.world, which is players, which would be our main data set. But a brief summarize of everyone is the players.cv, which is our main one, is just basically a data set that contains information about all NCAA players from 1947 to 2018, all seasons. Data set contains physical information on players such as height and their in-game statistics. The games data set just contains information of all games from 2004 season until 2021. The games details contains just details about every player, statistics, and given their NBA game. The NBA players data set contains basic player details such as their name, ID, team name, player ID, and season. Rankings obviously contains the rankings of their teams and standings. And teams data set contains information about the NBA teams, such as year and the year they were founded and abbreviations. Next slide, please. So the way that we formatted this project is that we use data cleaning, prediction models, and findings. I will be going over in the next previous slides about data cleaning. Next slide, please. So unfortunately, on like many data sets that in the real world, we don't get them as clean as we as we do in classes. So we had to do numerous amounts of data cleaning. As you can see, reading in the data, we have about 38 to 32 columns here that give us basically a lot of NaN values. And so we had to perform a lot of like data cleaning for this data set, which is a players.csv. Next slide, please. So here we are just basically formatting it as in like making it sure that it is readable to us. And so we don't get confused when our other group members was using it. Next slide, please. So as you can see from the previous slide, that most of the columns contain no values. All values of the NCAA column basically are null. Therefore, we disregarded the whole column. There are 2,508 non-null values in columns, NCAA games, points, and field goals and such like that. We basically assume that with the no values of NCAA games, that because they're in columns with NCAA games, some of them are null, we assume that they did not go to college. And so we basically just remove that column completely as well. Next slide. And I will hand it over to Richard for this one.
Okay, so I'll be covering basically EDA and general visualizations that we did. Our primary like research questions that we wanted to answer with this and like show is like how can we use readily available NCAA, NBA data sets and like data analysis to visualize and describe the data and their relationships basically. And so we wanted to compare the NCAA player statistics with the NBA player statistics and also answer how do players' physical attributes affect their performance and roles in the NBA. So with the first visualization in the top left, you can see we compare NCAA points per game with NBA points per game. And looking at this plot, there does seem to be a very noticeable positive correlation between NCAA points per game and NBA points per game. And can kind of be seen by the linear regression line. Also, it is noticeable that for the NCAA points, they cluster is more apparent in the 10 to 20 points range, while the NBA points cluster is in the 0 to 10 points range. And this does make sense intuitively, as it would be naturally much harder to score against the best of the best defenders in the NBA as opposed to as opposed to defenders in the NCAA. In our second graph over here, basically we're showing the games played in the NCAA versus games played in the NBA, which can be relevant because we can see like how much the teams are actually using the players that they draft, and this could be like useful for scouts. So it's interesting because we can see sort of like vertically where like the 4 years of NCAA players or NCAA player divided for players, and which after some further Googling, this lines up with like the 25 to 35 games that teams tend to play in the NCAA season. And we can see like a very slightly negative trend because like in the higher end of NCAA games played, there's a much larger groups of players that don't get to play games in the NBA at all. And this could support the idea that better players will often get drafted earlier in their careers, and so they'll play more games. In the third visualization, we can see comparing field goal percentage in the NCAA versus the NBA. In this plot, we can see a greater variation in shot percentages in the NCAA, but as the players move to the as they move into the NBA, this variation seems to be corrected once the players go against better defenders. And so in the NBA, we can see like the percentages, the shooting percentages seem to like coalesce into a smaller range around like and very strong near the 40% field goal percentage. Disregarding a few outliers, of course, we can see that even the best shooters in the NCAA become like a lot more average once they go to the NBA, percentage wise. But there's still a very slight positive correlation between the NCAA and NBA field goal percentage. In the bottom left graph, we graph 3-point percentage in the NCAA versus the NBA. This is just important because in today's game, the 3-point is a very relevant shot. So there are two noticeable things at first glance. The 3-point percentages between the NCAA and NBA seemed much more tightly bound and even between the leagues at around 30 to 40% for most players, and seem to correlate pretty strongly. The other noticeable thing is that either the players would be in the previously mentioned percentage range or would lie in the 0% range. This tells us that players that feel like they can shoot threes tend to have a decent average percentage at around 30 to 40%, and there will be therefore they will attempt more 3-point shots. On the other hand, players that don't have confidence in their 3-point shooting ability will not attempt any 3-point shots at all, which is why you can see a lot near like 0%, and they will attempt other types of shots. In the next one, we can see in the next graph we see 3-point attempts per game in the NCAA versus the NBA, and we can see that there's a similar trend as previous plots in that there are on average more 3-point attempts per game in the NCAA than in the NBA. We can observe that most players attempt between 0 to 6 3-point shots in the NCAA, while this gets narrowed down in the NBA, and over half of these players will decrease their 3-point shot attempts between to between 0 to 2 a game in the NBA, just because they're going against better defenders is what we infer. However, we still notice that there's a noticeable positive correlation between the two leagues, in that players who tend to attempt more 3-point shots that will carry over into the NBA. In the next graph, we do free throw attempts per game in the NCAA versus the NBA. This is interesting because it shows obviously a large discrepancy between free throw attempts made in the NCAA as opposed to the NBA. And there seems to be a huge number of players that take between 2 to 8 free throws a game, with average looking to be around 4 to 5, while in the NBA, the vast majority of players are within 0 to 2 free throws attempted per game. So as we see in the plot, as there's some Googling into how much more prevalent free throws are in the NCAA, yeah, it's just, yeah, we can see that the free throw is a much more prevalent shot in the NCAA. Next slide, please. So this first graph here is pretty interesting because we would expect that NBA player heights would affect points per game, but according to the data, that's not really the case. With the exception of like the lower end of the height scale towards the 160 to 170 centimeter range, there seems to be very little or maybe not even any correlation at all between the heights and points per game in the NBA. From this plot, it can be assumed that height is not so great of an indicator for how a player will do in their NBA career. And next to plots, we have NBA player heights that plotted against their rebounds per game and their assists per game. And so we can see in the rebounds per game, there's a more positive correlation. While in the assists per games one, we can see that there's like a negative correlation. To explain the rebounds per game, it would make sense that taller players will go for the rebounds, and we can see this upward trend. As the height increases, we'll see like the rebounds per game go up, which, yeah, makes sense. They're taller, they'll go for more rebounds. And for assists per game, we don't really, I didn't really expect for there to be any correlation, but from the plot, there does definitely seem to be a relationship between the two, and this could possibly be inferred because taller players could be rebounding the ball and will therefore have like less assists per game, while shorter players could be receiving these rebounds or receiving passes from the rebounders, and their role on the court could be to get the ball to other teammates in order to score the points. Next slide, please. I'll be passing it over to Ricardo.
After analyzing our data set with different data from different data sets, we looked into the data set that had performance stats from NBA and NCAA, and we noticed that there were a high correlation between NBA and NCAA stats, and also within the same league performance. And you can see that by looking into the heat map. And we use this heat map and a correlation matrix to identify and highlight the main correlations between each feature and each target column. Next slide. So once we had the data cleaned and the exploratory analysis, we moved into building the models, the machine learning models, and we wanted to basically compare those models and pick the best one that will perform better to forecast the NBA performance based on the player personal information and their NCAA performance. Different than what we used through the course where we looked at accuracy for a classifier. This time, we needed to find a metric to analyze regression models. So we looked into both R-square and mean squared error. And for the models, we chose 4 different models. We chose linear regression, random forest, or vector machine, and neural network. For linear regression, as we saw in the previous slide, where there was a high correlation between features. So we figured out it would be better to use the regularization method. So we use reach method to penalize some features and reduce redundancy in some features. We use grid search to find the best alpha for the reach method. In the random forest model, we also did a grid search to choose the best pruning parameter and also control for max features in each node split. The following one is for vector machine, similarly to the linear regression one. We wanted to reduce redundancy for features, so we control for the C parameter with the grid search again. And finally, the neural network, we tested different hidden layers, set up different number of hidden layers and different quantities of neurons, also using a grid search to pick the best setup for the neural network. And this table here shows us a summary of the performance for each model. As we were forecasting 12 different target columns, we aggregated the results in average and standard deviation for both R-square and mean squared error. The R-square ranged from 0.189 to 0.265, and the mean square error average ranged from 0.668 to 0.735. It's clear here that linear regression had the best performance out of the 4 of them. And in the next slide, we'll go into details for each target column. Next slide, please. All right, so we also plotted, other than the average and the standard deviation, we also plotted each target column, their R-square and their mean squared error. So we can look at the linear regression result, which was our best model. It has some volatility in both R-square and MSE, but we can see that it had the highest R-square score in general, even though the accuracy, the quality for each target column varied a lot. Next slide.
For research and conclusion. So after checking with EDA, linear regression, random forest, SVM, and neural network, we found out almost every performance statistics in the NCAA has some correlation with the corresponding performance statistics in the NBA. Therefore, it is reasonable to assume that the NBA performance can be estimated to some extent by using the NCAA performance data. Also, multicollinearity occurs between most of the NCAA columns, implying that the predictive ability of those variables is limited. Collinearity within NCAA features point for redundancy and limitation in the models. The best performing model on average among the tested is the linear regression model, ridge regression. It reaches the average R-square score of 0.263 across all of the NBA performance metrics. Variation in predictability of the NBA performance metrics is mostly similar for every model. The model predictable statistics are NBA 3P-TAPG, NBA 3P-TPG, NBA FGPCT, and NBA FTPCT. The ridge regression model is best used to predict NBA 3P-TAPG NBA 3PT-PG, and NBA FG-PCT with R-squared scores 0.405, 0.384, 0.314, and 0.326 respectively. The NBA FT-PCT matrix can be better predicted with a linear model based only on the NCAA FT-PCT matrix with 0.33 R-squared score. So every model had a higher variance of accuracy of target columns. We could try to improve the model by finding more independent features of NCAA performance. Thank you.